For the final talk of this afternoon, Kasra Rafi from Toronto tell us about geodesic currents and counting problems.
Okay, yes, thank you very much for the invitation and for the introduction. Yes, so as usual, the main object of interest, sigma, is a surface of finite type. Actually, let me just say closed surface. I do really need it to be closed. So Mark kind of set up the things I wanted to say a little bit, so I'm very happy about that. Yes, so we have the Teichmüllerspace of sigma, and then the Thurston boundary of this is often identified with the space of projectivized measured lamination. So since Mark didn't define this, maybe I won't either. So you'll see a little bit what it is in a second if you don't know. So to me, the correct way of understanding how the boundary of the Teichmüllerspace is PMF or PML, except for the length function, is through currents, so geodesic currents. So I want, first of all, I want to draw for you a picture of this boardification or compactification using the language of geodesic currents. So C of sigma is a space of a geodesic currents. So what do I mean by that? I mean, so the geodesic current is pi1 invariant Rodin measure on the space G of sigma tilde, which is the space of geodesic on the universal cover of sigma, right? So let's see what that means. So sigma is a topological object, but we say geodesics because I don't want to say paths. I want to make sure if I lift these objects, they have different endpoints at infinity. So you can fix some hyperbolic metric on sigma, then the space of geodesics on sigma are basically the space of pairs of endpoints on the boundary, right? So this object here is basically S1 cross S1, except that I don't want these points to be the same, so I have to remove the diagonal, and then I don't care about the order, so then I divide it by Z2. So this is the space of geodesics on a surface, and so a measure is just if I have a set of geodesics, I want to know what the measure is. They have to be additive and so on, and they have to be pi1 invariant, right? So very good, and then I give this a weak star topology. So let me do a few examples of the space of currents. So the main thing is you can think of points in Teichmüllerspace as geodesic currents. So there's the embedding of this space into this space. And there's also embedding of the space of measured lamination into this space. So let me tell you how that works. So examples. If I have a point X in the Teichmüllerspace, maybe just write Tg. This is the surface of genus G. Then here, let's just put sigma. So then the universal cover of X gives you an identification of this boundary. So when I drew this picture, what did I mean really? So this is a boundary of sigma. So this is kind of topologically defined. So basically, this is the Gromov boundary of the fundamental group of sigma, right? And if I have an actual hyperbolic metric, then the identification exists between this guy and H2, right? So then if I look at H2, then this can be thought of as the universal cover of X, which means the boundary at infinity of sigma now is identified with a unit circle in a particular way. So now if I have an open set, let's call it Ij with endpoints A, B, C, D, then I can look at a current, let's call it the Liouville current L of X, which assigns to, see, this is an open set in the space of geodesics. So gives the value log of the absolute value of the cross ratio, which is A minus C, B minus D A minus D, B minus C. I hope this is correct. Right, so this is, so identification between universal cover and H2 is defined up to Mobius transformations. They also preserve the cross ratio, so this is a well-defined object. So I have an actual measure on the space of geodesics. It's pi1 invariant, obviously. So this is what I call the Liouville current. So I can think of a hyperbolic metric as a measure on the space of geodesics, right? The map is 1-to-1 and so on. I'm going to write a theorem saying some of this stuff. Okay, so example number 2, if I have a lamination, yeah, maybe I change this, yeah, to PML, so it's laminations. So a lamination also, a measured lamination is also a current. So how do you do that? Well, a measured lamination is a bunch of leaves like that with a notion of transverse measure. So again, if I pick I and J, then I can look at the, well, it's really kind of like that. So I have to look at the measure of these arcs and subtract the measure of these arcs, and they give you a measure for the set, because I wonder how many geodesics start from here and end here, right? So they have to, every time start from here and end here, you have to either intersect this or that, except that the ones that you start from here and exit are these guys, and the ones that start from here and exit are these guys. You have to subtract them, and so on. So basically, if you have a notion of transverse measure on leaves, you know how many leaves you're talking about. So that is really a current, right? It's a pi1 invariant notion of measure. If you have a set of such things, like leaves of the lamination, you kind of know how many of them. Okay? So that's example number 2. And example number 3, weighted closed curves. So what do I mean by that? It's like maybe you have a curve like that, and maybe you have another curve like that, and you give this guy weight 2, and you give this guy weight 3. So this is an example of a weighted closed curve. Could be multi-curves and so on. So this is also a current, because again, if I have intervals I and J, I mean, you should think of this as having 2 of the red and 3 of the green. And you can again count how many of them start from I and end with J, and you get your measure. Define that. Okay, so many of the objects that we are interested in usually, like hyperbolic metrics, laminations, closed curves, weights and so on, they can be thought of as currents. And in fact, many of the ways these guys relate to each other can be thought of as currents. So this is done by Honohan. So let me summarize a bunch of these results at the same time. So the theorem is that there exists a pairing, bilinear pairing, which I call it intersection number, from C cross C to R plus. Maybe I should say continuous. So that's very important. Which has a bunch of properties. For example, so let me say, so if so in each of these situations, it has a particular meaning. For example, if I look at the intersection between a Riemann surface and gamma, where gamma is a closed curve, then I would get the hyperbolic length of gamma index. Right. If I pick 2 curves, gamma and gamma prime, here gamma and gamma prime are curves or closed curves, then this pairing, that's the reason for the definition of it, is the geometric intersection number. Let's do a few more. If an element lambda in is a measured lamination, then intersection of lambda with itself is 0, as you expect, because the lambda is made of simple curves. And in fact, this is a if and only if. This is a characteristic behavior. So if somebody doesn't self-intersect at all, then it has to be a measured lamination. There's nothing else. Is there anything else do I want to say? So the space of weighted closed curves are dense in C of sigma. So in fact, every current can be approximated by weighted curves. Okay, so this is very nice. So using this picture, we get a nice visual picture of Teichmüllerspace and the way the PML embeds in it. Because I mean, you should think of as your background image as H2 sitting instead of R3 in the Minkowski model for the hyperbolic plane. So this is again all to Bonahan. So you can visualize ML as a cone, as like a light cone sitting in space with currents. These are ones. So if your intersection pairing is like a norm, then self-intersection 0 is like having 0 norm. So that's like a light cone. And yeah, maybe I can write one more thing here. If a point is in a Teichmüllerspace, then its self-intersection of x with itself is just the volume of the unit tangent bundle or the line bundle. It's pi squared times the Euler characteristic of sigma. So it's some fixed constant. So this is basically like a sphere. So all the points in Teichmüllerspace sit here in this way. So they have a fixed norm. And then if I pick a sequence of points going to infinity, they converge up to subsequence to a ray, right? An array in ML is just a projective class of measured laminations. So they converge to element of projectivized measured lamination. So they converge to PML. So this is how you should see it. So there's a convergence in measures. If I go over here and I scale them down, they actually converge to a lamination like that, right? So this is the correct background picture that we have. So far we have decided that currents are nice because you can see lengths as intersection number. You can see the intersection like that. So many of the different topics that you can discuss, they're all like packaged together in this one language. So what I want to do is I want to, in fact, package together a bunch of counting problems that exist so far into one counting problem, and then explore its other applications, right? So, so I want to state the main theorem. So let me just write some more notations. So the ML has a natural measure. So on ML we have a notion of a Thurston measure. So what is Thurston measure? I mean, how do you see ML? So usually you have a train track and you have some weight system, and A is equal to B plus C. So you would find a way to embed ML inside of some Rn, right? And then the volume form coming from Rn defines a volume form on ML, which I call the Thurston measure. But for today, I want to say, there's also a symplectic form coming from this intersection patterns on the train tracks. So then that defines for me a volume form, which I call the Thurston volume, right? So maybe I call it Thurston volume form. So this comes from the symplectic measure, right? So, or you can think of this as locally ML sits inside of some r to the power of number of edges of the train track, right? And look at the restriction volume form. Okay, so using that, so this I denote by mu sub th, right? So this is a measure on ML, is a locally finite and very nice measure. Okay, and let's say alpha is, maybe I just put one piece of more notation. I would say an element, a current alpha is filling if for every other current the intersection of alpha and beta is non-zero. Right? So laminations are not filling. The currents which have support in the subsurface are not filling. Everything else is filling. Okay, very good. So the main theorem. So for every alpha which is filling, I define a quantity m of alpha, which is the Thurston measure of the set of laminations where the intersection of alpha and lambda is less than 1. Note that since alpha is filling, this is some compact subset of ML. If you multiply lambda by some big number, the intersection eventually goes too high. Right? And I define Bg to be the integral of mx with respect to the withThurston volume form over the moduli space. So this is kind of a standard thing to do again. So basically, I'm going to care about the ratio of these two things. So I want to know, right? So this is the average measure of such sets when x is varied over the moduli space, right? So that's how you should think about that. Okay. So very good. So theorem, and this is I'm first, but that's okay. It's a joint work with Juan. So let's say you have a f from C to R, which is continuous and homogeneous. So homogeneous just means f of k times alpha is k times f of alpha. And I want to do a nice counting problem like that. So I want to count the number of mapping classes phi such that f of phi of alpha is less than or equal to some number L. So I should say what alpha is. Alpha is a filling current. And the theorem says that if I take the limit of this as L goes to infinity, it basically grows like L to the power of 6g minus 6. And in fact, the limit of the ratio exists. And in fact, I know what the constant is. It's some constant depending on alpha, which I just defined, some constant depending on f, and this number Bg. Yeah, maybe I erase this and I put this little notations here instead. So this is, I'm going to explain what this theorem is by doing some special cases of it in a second. So, so m of alpha is the Thurston measure of set of lambdas, where intersection of alpha and lambdas are equal to 1. M of f is basically the same thing, is the Thurston measure of lambda, where f of lambda is less than or equal to 1. And Bg is integral of m of x with respect to the withThurston volume. Okay. Yes.
What's the element?
I'm sorry?
What's the element?
Phi is the element of mapping class group. That's MAP for mapping class. I know people don't do that, but that's Juan wants to do that, and I'm kind of sold on it. So that's the notation I'm going to use for mapping class group. Because I say mapping class group, so why not write MAP? Is the logic of it. So right, that's the map. Yeah, I should have said that. So MAP is the mapping class group. Yeah. So basically, you pick any filling current, and you pick any function you want, right? And you want to find the number of mapping class group orbits of this current, which have the value function is less than L. This always grows polynomially with the same exponent. The limit always converges, and exactly is can be written as a volume, Thurston volume of certain sets inside of the ML, right? Yeah. So let's do a few special situations of this theorem, so you would know what is going on. So this is a theorem of Maryam-Mirzakhani. So the special case here is, let's say your alpha is, let me just write, gamma is a filling closed curve, some complicated curve. So this is gamma, and x is a point in Teichmüllerspace. And then you want to find out how many different curves which are of this type are there of length less than a given constant L, right? So you want to find the number of elements phi in the mapping class group such that the hyperbolic length in X of phi of gamma is less than or equal to L. Right? So the theorem is that this grows, again, polynomial like 6g plus 6, and the limit exists. In fact, so Maryam proved that the limit has certain properties, but they actually can tell you what the exact value of it is. It's m of gamma times m of x divided by bg. It's this exact number. So the growth rate of number of curves of a particular type, gamma, of certain length, always grows polynomially, and the limit exists and is this exact number. So you can converge the limit. Okay, so the proof is pretty straightforward, I guess. I don't know if I should write it down. So basically, the main thing is, if I pick x, then hyperbolic length, so my f is hyperbolic length at x, which is basically intersection number of x with something. So that's my f. By theorem of Bonahan, this is continuous and it's clearly homogeneous because this is fixed, so I can just scale the other one. And I plug it into that formula, and that's exactly what I get, right? So since my function is intersection, then these two have the same type.
So somehow, in your theorem, the unit homogeneity does not play any role.
In the theorem, it doesn't look like it's playing a role. It doesn't. But I should bring the L over here, put 1 over L phi of alpha there, and that's why I get this set. It has to do with figuring out what the constant is. It relates it to this measure. Yeah, so I need homogeneity if I want to know what the constant is.
The K itself. I mean, this is true for any degree of homogeneity. So.
Yeah, that's correct.
And K is probably different.
That's correct. Then you would get a different power. That's right. That's correct. Yeah, I mean, like, so also you can replace, if you want to have intersection, you don't have to pick your x to be hyperbolic plane. So people who do higher Teichmüller theory, they have other representations. These things define, if I understand correctly, they're the determinant, or at least they have an associated Liouville current. So you can do the same counting problems for those guys, and you can count the number of orbits that a certain loop has a length less than something. So I don't have to put x and gamma here. I could put any alpha and any beta here, where alpha and beta are geodesic currents. So the same counting problem would work. So in fact, I should say, it's not that we prove Maryam's theorem. We kind of use her theorem very much. So so I'll get to the idea of the proof. So all of this work kind of relies very much on work of Maryam-Mirzakhani and also the I think Erlandson and Souto. So they have proven like special cases of the theorem. This is kind of like packages together and then proves in the most general setting, and also we find out what the constants are, which is which is new. And also stating them this way, you can consider like other functions. Right, so let me just do another application too. So this is a lattice counting problem. So look at Teichmüllerspace, pick a point x and another point y, and then look at the orbit points phi of y. Also choose a ball of radius r in some metric. So the metric I want to define here, since hyperbolic length is what behaves naturally with respect to currents, I want to use the hyperbolic length to define the metric, and this is done by Thurston. So I consider the Thurston metric on Teichmüllerspace. So there are two ways to define it. I can define the lengths, the distance between 2 points, to be supremum maybe over length ratio of the laminations. So look at the hyperbolic length at y of lambda and divide it by hyperbolic length at x of lambda, and take the supremum over all laminations, and take a log. That's right. Or, so the same as Teichmüllerspace, that has two definitions, or you can do infimum over all maps from x to y, which are in the correct homotopy class, and there are Lipschitz of log of LF, which is the Lipschitz constant. So Thurston proved that this equality exists, right? And this is a nice geodesic metric space. In fact, I've been studying this geometry recently. It's a very nice, exciting space to give it the advertisement. I mean, you can do everything you want to do with the Teichmüllerspace, but if you care about hyperbolic lengths, you don't have to go to extremal length and then come back. You could just study the space with this metric directly. So anyway, and it's a nice metric, but it's not symmetric. So the d of xy is not equal to d of yx. So that's similar to the outer space situation. So here the theorem is, yeah, maybe I should pick a different space for this. So for any pair of points x and y in the Teichmüllerspace, I can try to find the number of elements of the mapping class group such that d of x and phi of y is less than or equal to r. So here, the distance has a log in it, right? So the growth rate is exponential and is e to the 6g minus 6r. And the limit of this always exists and is equal to some constants you can compute. It has I write it m bar of x times m of y divided by bg. So the m bar of x is like basically m of f for some function which depends on f. So maybe I write that here. So if I define my f to equal to dx, where dx of alpha is basically this ratio, so is equal to supremum over lambda in ml of intersection of alpha with lambda divided by intersection of x with lambda. Right? So this supremum is what determines the distance, right? So I can just look at that without the log. Since it has intersections on the top and the bottom and supremum, this is a nice continuous function. It's homogeneous, right? So I can feed this into my theorem. Since it works for any function, the f of phi of y is basically e to the power of the distance in the Thurston metric between them. Maybe I should write that down. So given that, so I'm saying the distance between x and phi of y is e to the power of dx of y, right? So if I plug things into here, I have to just replace r, well, L to be e to the r, and apply the theorem.
The other way around?
I'm sorry? Yeah.
The other way around?
Say it louder.
The other way around.
The other way around. What do you mean? Like phi of L is e to the r. E to the, oh, log. Thank you. That's right. Thank you. Yes. That's right. So the distance is log of this function. So if I plug in r equal to e to the L, so the set of things which have a distance less than or equal to L is a set of functions where this d is less than e to the r. So we get e to the r to the power of 6g minus 6, which is exactly the function I have wrote. Right. Okay, so pretty diverse looking theorems. They all follow from our main theorem over here. So all kinds of counting problems can be done as long as the objects you have are somehow currents, which lots of objects are, and the function you have is some continuous function of currents, which lots of things are. So for example, you can ask, so there's a usual theorem, like the old version, like not old version, so this is the Atria Buffetov Eskin in Mirzahani, that if you want to do the same thing with respect to the, so count the number of phis where the Teichmüller distance between x and phi of y is less than or equal to r. Again, this grows exponentially. And the limit exists and is equal to I believe it has some form like this. Oh, then I divided already. Yeah, it has some form like that. And h, yeah, I think that's correct. Actually, I don't know why they have a h here, but it's somehow, it's kind of mysterious. It shouldn't be here. There's normal counting problems. But anyway, so h is the entropy. 6g minus 6. So there's a the usual counting theorem in the Teichmüllerspace gives you some function like that. And these lambdas are somehow defined similarly to what we have, but using extremal length instead of hyperbolic length. So these are called the Maser-Witch function on Teichmüllerspace. And later David Dumas proved, in fact, that these are constant functions. So in the case of Teichmüller metric, the constant that you would get does not depend on x and y for some weird reason. But in our case, it actually does. These functions m and m bar in no way are constant. In fact, they blow up. They go to infinity as your point goes to infinity. So, yes. Right. But anyway, so to prove this theorem, you have to do a lot of hard work. This uses the dynamics of the Teichmüller flow and so on, right? So it's not a completely easy theorem to prove, and then our theorem is kind of much easier in some sense after you know how to prove that. So there is some convergence here, but it's like much easier after you know the theorem of Mirzahani. So basically you have to prove some limit converges, and the first thing that you can prove is that theorem that Maryam has proven. And after you know that, then I'm going to state the actual theorem that we prove. You can prove sequence of measures converges, and then you can do all kinds of counting problems all at once. Right, so that's the equation, corresponding theorem to this, except this is extremal length and that's hyperbolic length. So otherwise it should look basically the same. Yeah, any questions so far? So if not, I'm gonna like say the actual theorem that we prove, which has this as a consequence. So I'm gonna try to state that. So let me draw back for you the Bonahan's model of Teichmüllerspace. So this is TG, this is ML, and then there's a group action here, right? So the mapping class group kind of acts on this space, right? Fixing the light cone and fixing the Teichmüllerspace. And then the orbits of points have the discrete orbits, right? So the fact that the points in Teichmüllerspace have discrete orbits, it means any other point, as long as it's not in the light cone or is filling, also has discrete orbits. The points in the light cone are possibly, if you have a Pseudo-Anosov, has attracting and repelling fixed points here. So points could really come close to the origin. So the action here is by no means discrete, but everywhere else it basically is. So if I pick any filling current alpha and look at its orbit, it kind of fellow travels the Teichmüllerspace in this way, right? So if I pick this orbit and then I scale it down, it basically gets closer and closer to the light cone. And I want to say in the limit it converges, in fact, to the light cone, right? So for every alpha, let delta sub alpha be the delta measure for lack of a better name on C. So this is a measure on the space of measures, right? So it's a measure which gives you 1 point here and 0 everywhere else. And then I look at the, so for alpha filling and L positive, I define this new L of alpha to be the following sum. So I look at the delta measure at phi of alpha, but I want to scale it by factor L, and then sum this up over the whole mapping class group. So basically I put a delta measure at every of alpha, then I scale the whole thing down by factor L, so I would get a light, basically a green light everywhere here near the light cone. And then of course a lot of them will come really close to 0, so I have to scale this down to get the measure to converge. So this is new alpha L, this is a measure on the C, and the theorem is that the limit of new alpha L as L converges to infinity is equal to the Thurston measure times this number m alpha. So this sequence of measures converges. So this is the real theorem you have to prove. I mean, this kind of sums are written in homogeneous dynamics, but I've never actually found this exact analog of this one. So if somebody knows, they should tell me. But very, very similar sums have been written.
This is proved by Rufus Bowen.
By whom?
Rufus Bowen.
No, it's not. I looked at Bowen's. I couldn't. We can look together. Yeah, I taught Bowen, and also I taught letter P. They have very similar sums. It's not identical to this. Yeah, you should if you can pinpoint an actual thing, you should show me. Yeah, that would be good.
He proves that the Margolis measure is equal to this limit, and that's
right.
proven here.
No, that's right. So the idea of looking at this kind of sums is very prevalent, and there are many sums like that. In fact, that's true. Yeah. So, and then Teichmüllerspace supposed to get ideas from the homogeneous dynamics. So this is our attempt to do that. So, but again, so the picture that you have is that the green lights are following this guy. So if I shrink them down, they converge to the light cone, and the support. So this is a measure on the whole space of currents. This is a measure with support only on ML. right? So in particular, it says the support of this is in ml, and in fact, it's in Lebesgue measure, and it has this exact constant in it. Right. Okay, so I have 10 more minutes. I can say two things here. So the first question is, what is the outline of this? And the second question is, how do we find this constant? So there are two different things which go to each of those. Yeah, maybe I'll erase the A-band paper. So let me give you the outline of the proof. So the first thing is you have to prove this guy doesn't blow up. So the family mu alpha L is precompact. So this is true for the following reason. First of all, if I put X here, then I would know that this family doesn't. I mean, there is one part I skipped, which is how do you get from here to there? But this is not really hard, actually. If you write that counting problem as measure of some set associated to some particular ball, the convergence of this measure is exactly saying that this is a delta measure, so it's a counting measure, right? So, right. So anyway, so if you know a particular limit exists, then you would know that this guy cannot blow up. So if I have alpha equal to x, I know by theorem of Mirzakhani that this limit exists. And if I pick a different alpha, alpha and x have intersection numbers which are bounded away from each other because by some compactness. So if this for x does not blow up, for any alpha which is filling, also doesn't blow up. So here is where we use the Mirzakhani theorem. So that's very good. So you have a limit. So if I pick any limit for any limit mu, so we show that support is a subset of ML. Right here. So how do you prove that? This is relatively easy. If you look at this picture, this becomes very clear. The support of these guys are in some cloud which fail travel as a Teichmüllerspace. If I shrink the Teichmüllerspace down, it converges. And this is some bounded distance away from it. In fact, for any open set you pick, these guys will miss it eventually for large enough L. The whole cloud lives in a small neighborhood of the ML. So this is not so hard. So then you have to say that the mu is equal to some c times the Thurston measure. So now you have a measure which is supported on ML only. And you want to prove that it's a Thurston measure on ML. But here we have a classification. So the good thing about this measure is, the way it's defined, is mapping class group invariant. Right? So you have a mapping class group invariant measure on ML. So there's a classification of such things by Mirzakhani and Lindenstrass. So basically they say it either has to be the Thurston measure or it has to be something like the Thurston measure coming from a subsurface. There's nothing else. But the ones that come from the subsurface, again, since we have a counting problem holds for alpha equals to x, we know that the things coming from the subsurface, they would give you a lower countings. So they would not give you the correct answer. So you could not possibly be one. So just by process of elimination. So it cannot be something which comes from the subsurfaces. Since you have a list of things, just eliminate all the bad guys, and the only thing left is the Thurston measure, right? So very good. And then you have to decide what this C is, right? So what is C? So to compute what C is, I have to tell you one more piece of the puzzle. Oh, maybe I want to keep the main theorem. We can get the application. Here I have this written as a note. Yeah, so yeah, basically let me just rewrite the theorem of Mirzakhani. So she showed that if I define, we just write nx gamma, so the L, well, yeah, let's do this. The limit as L goes to infinity of number of phi's where hyperbolic length of x and gamma is less than or equal to L, so divided by L 6g minus 6. So let's say this is the number that we are interested in, which is the constant associated with that. So what Maryam proved was that the integral of this guy with respect to the Weier's-Peterson volume is equal to, yeah, what did she prove? Yeah, actually, like, let me not do that. That's like one level of detail that I don't want to get. So she proved that this is some number depending on gamma, and this exact mx that we defined divided by bg. So she kind of knew all the pieces of the puzzle except for this one, and then she also computed the Weil-Peterson volume of B gamma, which I'm going to define it a little bit. Maybe I don't do it now. So if B gamma is the set of points x in Teichmüllerspace, where the hyperbolic length of x at gamma is less than or equal to R, yeah, she proved that this volume is basically e to the 6g minus 6 R times n gamma. Yeah, I'm sorry for the too much details here. So I want to say is, so we proved that this number is m gamma. This is our main contribution to finding constant, because Maryam already know the rest of the ingredients. And she also knew that this number n gamma has to do with the Weier's-Peterson volume of certain set. And the set is a naturally defined set, the set of all points where the length of gamma is less than R. So basically, instead of looking at the mapping class group orbit of gamma, which has a length less than R in X, you fix gamma, you look at the set of Teichmüllerspace, which gamma has a length less than that, and you compute the Weier's-Peterson volume of that. So to compute this, I would have to just have a better way of computing this, this volume. And so this is exactly what we do. So I guess my last little theorem here is to answer to what is C. We show that the Weil-Peterson volume of B gamma is asymptotic to n gamma to the power of L 6g minus 6. So this is the last bit. So since I don't have so much time, I'll just say in one sentence how this works. So basically, it turns out that if I look at this set, not in Teichmüllerspace, but in shearing coordinates, then the image of this in the shearing coordinate of some lamination lambda is a very nice convex object, actually. And the Weil-Peterson volume turns into the, because the Weil-Peterson volume comes from the symplectic form on the Teichmüllerspace. And the map, which the shearing coordinate map, actually sends the symplectic form for the intersection number exactly to the Weil-Peterson symplectic form. So the Thurston volume mapped exactly to the Weil-Peterson volume. So I can compute the volume in the shearing coordinates. And there I can actually scale things back. And if I prove my set converges to this setwise, and it's a nice convex set, the volumes actually converge. So I can compute the volume of this relatively easily. And then since, because of the Maryam's theorem, that tells me what this constant is, which I can fit in to my theorem and then figure out this constant is m alpha over there. Okay, that's all I want to say. Thank you very much. I'll stop. Yes.
So in terms of Thurston's metric, is the metric convex for the Thurston's metric?
Say it one more time louder.
Balls in the Thurston's are symmetric, metric, convex. So
Convex, who knows?
how does this behave as a function in Teichmüllerspace?
No, the balls could be pretty nasty. I mean, yeah, there's no good control of how the balls look like, because potentially you could go into the thin part and then stick out somewhere and have some weird piece. No, I mean, there's no information here about the ball. In the shear corner, they looks nice. In actual Thurston metric, they don't. I doubt they're convex. Yeah, I mean, in Teichmüllerspace, the balls are not convex, right? And here, it's clearly, I mean, yeah, you can clearly put examples where some geodesic goes out. This is not a unique geodesic space. They may be weakly convex. That's, I don't know.
Another question is, can we estimate the constant dg?
Can I estimate,
The constant dg.
like, how does it grow? It's, yeah, I mean, yeah, maybe. I mean, but it's complicated. I mean, it has to do with the Weyerson volume, right? Times some function which goes to infinity. The function goes to infinity kind of slowly, so the integral converges. Yeah, so no. I mean, I can estimate it, but basically the Weyerson volume is a good estimate already. Because in the thin part, the going to infinity doesn't matter so much, and in the thick part, is just some fixed constant. So roughly, this is just the Weyerson volume, whatever that is.
Question?